All right, we're going to start sections 11.3 and 11.4, which covers, which gets into square roots. And we're going to add it with the previous material before we have our test. So section 11.3 is about rational square roots. And these would be square roots that are either perfect squares or square roots that have, that come out as fractions. They wouldn't be irrational square roots, because those would be decimals that never end and never repeat. Basically, these are nice square roots. Okay, so example 1. I don't know if you remember doing this, if we did it in Excel math or way back in chapter 4, I think, but when you take the square root of a fraction, it's like you're taking the square root of the numerator and the square root of the denominator separately and just putting them together. So the square root of 81 is 9, the square root of 16 is 4, so 9/4. Example 2. You may see negative signs, well, not may, you will see negative signs on some of the problems, and that's preparing you for some things that are going to come in a few sections ahead. So don't worry about them, just if there's a negative in the front, it's going to carry through to the answer. So the negative square root of 100 over 49 is going to equal negative, the square root of 100 is 10, the square root of 49 is 7, so negative 10/7. Let's do square root of 144 over 441. Well, the square root of 144 is 12, and 441 actually is a perfect square, which goes down to 16. No, that's 21, I'm sorry. 21. Now, if the fraction simplifies, you want to keep going, because I can divide top and bottom by 3, and I'm going to get 4/7. Okay, now, if you have something like this, you have a fraction and you know that you don't have either one or both, the numerator and the denominator aren't perfect squares. Look to see first if you can simplify. I can divide top and bottom by 2, and I'm going to get 1 over 16. So really, I have the square root of 1/16, and then the square root of 1 is 1, the square root of 16 is 4. So you're going to have some that you need to simplify. Examples. As a matter of fact, most of them might be simplifying ones. 24 over 54. So neither of those is a perfect square, but I can divide the top and the bottom by, let's see, 6. So dividing by 6, I'm going to get 4 over 9. Still in the square root. I'm just simplifying the fraction underneath the square root. Now I can take the square root because those are both perfect squares, so that's going to give me 2/3. So simplify any fractions first. All right, that is, oh, no, a couple more types, hold on. If you have the square root of a decimal, you want to write the decimal as a fraction under the square root. So this is 16/100. I'm going to write it as 16/100. Now you can do what we did above, is take the square root of the top and the bottom. So top is 4, bottom is 10, so 4/10, which would be 2/5, or 0.4. The problem is when people try to take the square root of a decimal, they're likely to say 0.04 instead of 0.4. So it's best to just make it into a fraction first and then find the square root. And negative square root of 0.49, 49 hundredths. All right. So the temptation would be to say 0.07. Let's see. If I rewrite this as 49 hundredths, because the 9 is in the hundredths place, those are perfect squares, so I get negative 7 tenths or negative 7 tenths, right? So it's not going to be 0.07. And that's pretty much all of 11.3. These are mostly nice square roots. You might have to simplify, you might have to write them as fractions. All right, now I'm going to turn the page. Now it's hard to see through. Section 11.4 is irrational square roots. And these would be square roots that if you were to do them on your calculator, for example, you get this really long decimal, and in reality, they'd be decimals that never end and never repeat, just like pi. But we instead are going to be simplifying them. So let's see, which ones do I want to do? Let's start with the square root of 75. Okay, so not a perfect square. What you're going to do is make one of these little factor trees where you break it down. Doesn't matter how you break it down. I'm going to divide by 25, 3, and whenever you hit a prime, circle it. This is going to go 5, 5. And we're going to write all the factors under the square root. 3 times 5 times 5, like that. Well, whenever you have a pair of numbers under a square root, like this, 1 5 is going to come out of the square root. Because if you think about 5 times 5 is 25, right? And the square root of 25 is 5. Well, those two 5s basically make a perfect square. So for every pair, one member of the pair will come out, and you're going to put them in front of the square root. So it's going to become 5 times the square root of 3, simplified. Now, if I were to do that on the calculator, 5 times the square root of 3, you can see that's going to be a decimal. Or if I did it square root of 75, unsimplified, right? You get this long decimal that never ends and never repeats. There's going to be a little piece that's left under the square root because it's irrational, but we're simplifying. I think we did this when we did Pythagorean theorem last year, or at least some of you did. Okay, example 2. Square root of 98. Now, I think, it looks like it's divisible by 4. Let's see, 98, and nope, actually, it is not. So we'll divide by 2, and I get 49. So 2 is prime, I'm gonna circle that. And then 7 times 7 is 49. So I'm gonna write it with all its factors. These are all the prime factors. Look for the pairs, and one member from that pair will come out. And once you pull it out, it's probably good to do that so that you don't think either of these is left behind. They're gone from under the square root. Same up here. Once you pulled 1 5 out, that is gone. And the 7 that came out is going to go in the front. So this is going to equal 7 times the square root of 2. Simplified. Let's do 324. Okay, so if I break this one down, I think I'm going to break it by 4. And dividing by 4, 324 divided by 4 is going to give me, oh, that's nice, 81. Now there is a way to stop here, but I want to show it to you this way first. 9, 9. So 2 2s, 2 9s. These are all my prime factors. Oh no, that's not prime. What am I doing? 3, 3, 3, 3. There we go. So listing them all out, 2 times 2 times 3 times 3 times 3 times 3. There's a pair, so 1, 2 is going to come out, and that's gone. There's a pair, 1, 3 is going to come out, that's gone. There's a pair, 1 more 3 will come out, and that's gone. Now you have more than one thing coming out, so 2 times 3 is 6 times, that's 18. Is that a perfect square? Oh, that's a perfect square. Oh well. I can't put it in the front. This one I didn't realize was a perfect square. So that's going to be 18 exactly. Never mind. Okay, let's do this one. Sample 4. 2 square root 112. So there's already a 2 in the front, but we're just going to leave it there for now. So 112, I'll divide by 4, and that's 28, right? Yep. 4 times 28, that's going to go to a 2 times 2. 4 times 7, and then 2 times 2. So leaving the 2 in the front, I get 2 times 2 times 2 times 2 times 7. Circle the pair, a 2 comes out, cross it off. Circle the pair, a 2 comes out, cross it off. That 7 can't come out. He's stuck underneath. He's left over. So he stays put. These 2 2s come out, and they're going to multiply together. Just like up here, when these came out, these all multiplied together to get the 18. So I'm going to have 2 times 2 is 4, and they're going to multiply to the 2, which is 8. 8, and a 7 is left over underneath the square root. 8 root 7. Okay, let's do, that was example 4. 5, 192. All right, I think I can divide that by 4. So 192, 4 is going to give me 48. That's fine if you use a calculator to do this. If you noticed here, when I was showing you for the first time, I wanted to write all these individual pieces out. But if you find that you come to a perfect square, you can stop and circle it. And that will actually save you time. 48, for example, if I go, yeah, let's divide this by 3 and I get 16. If I see a perfect square just like here, I'm going to stop and circle it. So you could go all the way to primes, or if you see a perfect square, you can also stop. Because when you put them under the square root, I have 3 times 4 times 16. Well, the 3 can't come out, so he's stuck. The square root of 4 is 2, so a 2 is going to come out. The square root of 16 is 4, so a 4 is going to come out. Then you multiply these together and put it in the front. So that's going to be 8 root 3. It's a little shorter to stop with the squares. Now let's say I did the same thing, but I went all the way down to the primes. So 4, 48, 2, 2, 3, 16, but that's not prime, so if I did 4 and 4, you have a lot more little pieces this way. But if you're more comfortable doing that, that's fine. So 1, 2, 3, 4, 5, 6. That's 6 twos. So 1, 2, 3, 4, 5, 6. Let me make sure 1, 2, 3, 4. Yeah. Times a 3. There's a pair. 1, 2 comes out. There's a pair. 1, 2 comes out. There's a pair. 1, 2 comes out. 2, then multiply these and put it in the front. 2 times 2 is 4, times 2 is 8, so I get the same thing. So it's faster if you stop when you see squares. Okay, I think, let me make sure this one isn't a perfect square. 684, no. Example 6. The square root of 684. So it looks like I can divide by 4 for sure. Now 4 is a perfect square. Even though it's not primed, I can stop. 171, that's a weird number. Ooh, but 1 plus 7 plus 1 is 9, so I know this is divisible by 9. Okay, I can divide by 9 and I get 19. Well, I'm gonna stop here because 9 is a perfect square and 19 is prime. So when I put those under the root, I get 4 times 9 times 19. Well, the square root of 4 is 2. The square root of 9 is 3. 19 doesn't have a pair, another member of a pair, and it's prime, so he's stuck. Or it doesn't have a square, it's not a perfect square. 2 times 3 is 6, that goes in the front. 6 times the square root of 19 is the answer.